Lesson 3, the Binomial Theorem. Let's start by having a look at Pascal's triangle. When we're creating Pascal's triangle, we start at the top, and each row will start and end with a 1. So row 3 starts with a 1. The middle term becomes 1 plus 1 is 2 and ends with a 1. The fourth row starts with a 1. The next term is 1 plus 2 gives us 3. 2 plus 1 gives us 3, and the row ends with a 1. And we can continue that pattern down. It relates to combinations because 1 is just 0, C0. In the second row, we can write 1 as 1, C0 and 1, C1. The third row, 1, 2, 1, we can get from doing combinations of 2, C0, 2, C1, 2, C2. So that row, although it's row 3, our n value is 1 less than that. So the n value in those combination coefficients are all 2's. And then we start at 0 and count upwards for our r values. The fourth row, our n value is 3 all the way across the row, and our r value starts at 0 and goes up to 3. If we look at it a binomial expansion, so binomial expansion is going to give us a shortcut for expanding something like x plus y to the power of 4. Instead of having to expand it all by distribution, we can use the binomial theorem. So x plus y to the power of 0, if we start in the top, well, anything to the power of 0 is just 1. X plus y to the power of 1 works out to be 1x plus 1y, and you'll see that these are the coefficients from row 2 of Pascal's triangle. X plus y squared, if we were to distribute it, becomes 1x squared plus 2xy plus 1. And so the coefficients, again, come from Pascal's triangle or from using our coefficients using combinations. If you look at what's happening to the exponents, we have x squared. This is like having y to the 0. The power of the x decreases as we move to the next one, so it goes from 2 to 1. The power of y increases, so it goes from 0 to 1. When we move to the third term, we would also have here an x to the power of 0, which is 1. So let's skip down to the fifth row here. We have x plus y to the power of 4. Our coefficients come from the fifth row of Pascal's triangle, or from our combinations, where we're starting with n being 4. Look at what happens to your exponents. The exponents for your x start at 4, go down to 3, 2, 1, and this last term would have an exponent of x to the power of 0. Your y exponents start from a power of 0 here and increase to 1, 2, 3, and 4. Coefficients in a binomial expansion can be determined from Pascal's triangle. So in the expansion of x plus y to the n, the coefficients of the terms are identical to the numbers in the n plus 1 row of Pascal's triangle. So expand p plus q to the power of 6 and identify the patterns. So the first thing we need to do is to actually find the numbers in the seventh row of Pascal's triangle. So if we were to start building Pascal's triangle over here, we'd have 1 at the top, 1 and 1 in row 2. 1, 2, 1, 1, 3, 3, 1, 1, 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we end with the 1. Then we have 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and end with a 1. Remember that this very first row is the exponent 0, so this would be the exponent 1, 2, 3, 4, 5. So we need to go one more row. Again, start with a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And we end with a 1. So this will be the coefficients of our expansion of p plus q to the power of 6. So the first coefficient is a 1. Then we're going to have p to the power of, remember that our exponents for p are going to start at the highest power. So it's going to start at 6 and they're going to decrease with each term. Q is going to start at 0 and increase. Our next coefficient is 6. So the power of p decreases, so it moves to 5. The power of q increases, so it moves up to 1. 15 to the power of p now is down to 4, q is up to 2. 20 is our next coefficient. P decreases to 3, q increases to 3. 15 is our next coefficient. P decreases to 2, q increases to 4. You'll notice that my exponents always add up to 6. The next term, the coefficient is 6. P is down to an exponent of 1. Q is up to 5. And the last coefficient is 1. Well, if p to the power is 0, q to the power of 6. The last step is just to do some simplifying of those. So if I have 1, p to the 6, q to the 0 is just p to the power of 6. The next one, no simplifying to do, so 6p to the power of 5 q, we usually don't write the 1. 15 p to the power of 4 q squared plus 20 p cubed q cubed plus 15 p squared q to the power of 4 plus 6 p q to the power of 5 plus q to the power of 6. And there's my expansion. We can now look at some patterns in that expansion. So the first one is that there are 6 plus 1 terms. Right, my exponent of my expansion, we expanded p plus q to the power of 6. So the number of terms that I have here is 1 higher than this exponent. We already talked about the powers of p decreasing by 1, so they start at 6 and go down to 0. The powers of q increase, starting at 0 and go up to 6. Our coefficients are also symmetrical, so we'll look at 20 is our middle term, and the pattern is the same on both sides. Our binomial theorem says that if we are expanding x plus y to the power of n, this is the pattern that it follows. It becomes C0, and our exponents decrease. You'll see what happens to our coefficients, go from NC0 to NC1 to NC2, and so on. We can use the binomial theorem to expand any power of a binomial expression. Example number 2. Use the binomial theorem to expand 2a minus 3b to the power of 4. Okay, to expand 2a minus 3b to the power of 4, so part A, our first term is going to come from, if we use the combinations coefficients, 4, because my exponent is 4, so it becomes 4c0 as the coefficient. The first term inside my brackets is going to be raised to the power of 4, so it becomes 2a all to the power of 4. The second term is negative 3b, and that is to the power of 0. So there's the first term. The second term, my coefficient becomes 4c1. I end up with 2a to the power of 3. It decreases by 1. And negative 3b to the power of 1. The next term, I'll leave some room. becomes 4c2. 2a to the power of it was 3, so now it's down to 2. And negative 3b was at 1, now it's squared. The next one is 4c3. 2a to the power of 1, it decreases by 1, and negative 3b to the power of 3. The next term, 4c4, so we're at our last term, 2a to the power of 0, and negative 3b to the power of 4. I'm going to change colors and we can do some simplifying. So 4c1 is just 1. 2a all to the power of 4, well 2 to the power of 4 is 16, so I end up with 16a to the power of 4. Negative 3b to the power of 0 is just 1. My next term, 4c1 is 4. 2a to the power of 3 becomes 8a to the power of 3. And negative 3b to the power of 1 will stay as negative 3b. Moving to the second row, 4c2 is 6. 2a squared becomes 4a squared. Negative 3b squared becomes 9b squared. 4c3 is 4 times 2a times negative 3b all cubed becomes negative 27b cubed. Our last term, 4c4, is 1. 2a all to the power of 0 is just 1. And negative 3b all to the power of 4 becomes 81b to the power of 4. So let's put it all together. In that first term, I have 1 times 16a to the 4 times 1, which is just 16a to the power of 4. In the next one, 4 times 8 times negative 3 is negative 96, a cubed b. Our next term, 6 times 4 times 9, is positive 216, a squared, b squared. The next one is going to be minus 216, a b cubed. The last one comes from this last term, so it becomes positive 81b to the power of 4. So there's the expansion of that binomial. Part B asks us what is the third term in the expansion of 4b minus 5 all to the power of 6. So let's give ourselves some more room. Part B, we're looking for the third term, and I'm going to rewrite that binomial here. 4b minus 5 to the power of 6. If we're looking for the third term, our coefficient's going to be start with 6c. The third term in that row, first one starts at 0, 1, so the third term would be 6c2. The exponent for the third term, again it starts at 6, 5, so this one would be 4. The term is 4b. The next one has to add up to 6, so it's going to be 2, and that term in there is negative 5. So now we just need to expand it. 6c2 is 15. 4b all to the power of 4 is 256 b to the power of 4. Negative 5 squared is positive 25. Multiplying out gives me 96,000 b to the power of 4. So that will be my third term. Part C asks us in the expansion of, let's go back and look at that, a squared minus 1 over a to the power of 5, which term in simplified form contains a? Determine the value of the term. So we could look at the patterns that arise. Again, we'll get some more room. So for part C, we're looking for which term has the value of a. So if we look at the first term in that expansion, it would be 5c0, be a squared to the power of 5, 1 over a to the power of 0. And so the coefficient, the a value, a squared to the power of 5 is a to the power of 10. 1 over a to the power of 0 is 1. So this term the first term would include a to the power of 10. Let's look at the second term. The second term would be 5c1, a squared to the power of 4, times 1 over a to the power of 0. To the power of 1. So from this part, we end up with a to the power of 8. From this part, we end up with 1 over a, and so we end up with a to the power of 7. The third term would be 5c2, and it would be a squared to the power of 3 times 1 over a squared. So a squared to the power of 3 is a to the power of 6 times 1 over a squared. So this one would be a to the power of 4. And so my exponents for a in the pattern is that they are decreasing by 3. This means that my next term, or the fourth term, would be the one to contain a to the power of 1. We can check that by figuring out that next term. So I would have 5c3. It's a squared to the power of 4 this time, and 1 over a cubed. I'm not worried about what my coefficient is, because we were just looking for which term number works. A squared to the power of 4 is a to the power of 8. 1 over a cubed. What did I do wrong? Oh, I increased this one. This one should be a squared, which makes this a to the power of 4. When I simplify these two terms, I end up with a, so it is the fourth term in that expansion that contains the letter a.